Is Arctic ozone depletion seasonal? Have you ever wondered how the ozone layer in the Arctic changes with the seasons? The answer is yes, Arctic ozone depletion is indeed seasonal. This phenomenon mainly occurs during late winter and early spring. The unique atmospheric conditions during these months play a significant role in this seasonal pattern. Ozone depletion happens in the Arctic stratosphere primarily when temperatures drop low enough to form polar stratospheric clouds. These clouds are crucial because they provide surfaces for chemical reactions involving halogen compounds. These reactions lead to the destruction of ozone molecules. The critical temperature for these clouds to form is around -78°C. Interestingly, the Arctic stratosphere tends to be warmer than the Antarctic. As a result, polar stratospheric clouds form less frequently and extensively in the Arctic. This leads to less severe ozone depletion when compared to the Antarctic ozone hole. Typically, the depletion of ozone peaks in late winter or early spring, around March. This timing aligns with the return of sunlight to the polar region. The sunlight triggers photochemical reactions that speed up ozone destruction. After this peak, ozone levels usually recover as temperatures rise and the sunlight-driven chemical reactions begin to slow down. The extent and severity of ozone depletion in the Arctic can vary from year to year. This variability is influenced by atmospheric dynamics. Planetary-scale atmospheric waves can affect temperature and circulation in the stratosphere, impacting the formation of polar stratospheric clouds and the transport of ozone. Strong wave activity can warm the polar stratosphere, which reduces ozone loss. Conversely, weaker wave activity can create colder conditions, leading to more depletion. Recent observations indicate that Arctic ozone levels can be quite variable. In some years, ozone concentrations have even reached record highs during spring and summer months. This variability is partly due to unusual stratospheric weather patterns. The precise causes of these fluctuations are not fully understood, but they are linked to complex interactions between climate factors and atmospheric circulation. Looking ahead, the overall trend suggests that ozone depletion in the Arctic may weaken over the coming decades. This is largely due to the decline in ozone-depleting substances following international agreements like the Montreal Protocol. However, ongoing climate change adds complexity to this situation by cooling the stratosphere. This cooling could enhance the formation of polar stratospheric clouds and lead to increased ozone destruction. The balance of these effects will shape future seasonal ozone depletion patterns in the Arctic. In summary, Arctic ozone depletion is a seasonal event occurring mainly in late winter and early spring. It is driven by low temperatures and chemical reactions on polar stratospheric clouds. The severity of this depletion varies yearly based on atmospheric conditions, and future trends will depend on both chemical recovery and climate influences. Understanding this seasonal cycle is essential for assessing the health and climate impacts in the polar regions.